Share screen. All right, so Chapter 2, Research Methodology. So there's different ways of knowing. This is one of the things that I added into the textbook, by the way. I like pointing this out. In fact, there's a whole philosophy. It's called epistemology, if you're interested in such a thing. Epistemology on ways of knowing. How do we know anything? One is intuition. That's like, I think this is true. It kind of feels right to me. But it's actually not a very good way of knowing. But people use it a lot, of course. We'll use that a lot because it feels as true. Yeah. And authority is another one. Someone is saying this is true, therefore it must be, because they give this person authority. There's a lot of those as well. That's kind of probably one of the main ways people know things. Is they'll have, well, I mean, you have your textbook, for example. You have your textbook on psychology, and you give it the authority that it knows what it's talking about, which it does, by the way. Or parents, other teachers, what have you. Self-knowledge, knowing who you are, what you like. What you want to do, all those sort of things about who you, excuse me, are as a self. It's another type of knowledge, a very specific kind of knowledge about who you are. Logic is sort of deductive reasoning. So logically, this should occur. Let's say, well, if you have a supposition, a proposition that every male in Seattle likes coffee, which is probably pretty true. Or well, actually, here you go. This is even better on coffee because this is even more true. Almost everybody who smokes cigarettes drinks coffee. Joe smokes cigarettes. Therefore, it is very likely Joe drinks coffee. That's true. That's logic. You can know that Joe is likely to drink coffee or drink coffee if he smokes cigarettes. That's true, by the way. Like 95% or more of people who smoke drink coffee. We don't really know why. And then science. Science is a systematic way of examining the external world. It makes an assumption that there is an external world. Some philosophies would, whereas no one would not agree with that. They would say there's only consciousness, an internal world, and the external world is just essentially a manifestation of consciousness. Science will say, well, no, we don't think so. There is an external world, and we can know it, sorta. What does it do? Well, it describes, it wants to predict, control, and explain. So I think science is a really good way of knowing, okay? It's a really interesting way of knowing. And it's not easy. We don't think scientifically, really. We don't really, we as in humans in general is what I mean. We have a hard time thinking in the way science actually has you think. But it has a specific process of collecting data. That's the research part. And then with that data, you publish it. The idea is that you publish your papers, and that's how you communicate your science with everybody else. That's the idea. So here's this scientific inquiry. This nice little picture here showing all that. Let's see, I might get my pin back. But you start off with the theory. Actually, you start off with observation. Observation. Not very well spelled out, but you can see it. Observations. You have observed. I have observed something. And from that, you'll start saying, well, why is that happening? What is going on here? And therefore, you start making a theory. I think this is what's going on. And then you have a hypothesis, a very specific prediction based on that theory. And then you do the research. You test it in various different ways. Okay? And there's various different ways you can do that. You collect data, assuming that it's a quantitative research. Actually, qualitative does too. Collects data. It's just more. It's not so much numbers as it is stories and things. You then present it somehow in some kind of public way. So it either supports the theory or does not support the theory. You either reject the null hypothesis or fail to reject the null hypothesis. That's what you say. The hypothesis is basically, we think this is going to be the case. This relates to that. And the null hypothesis, it does not actually relate to that. So that's there's no relationship between something and something else, whatever it is you're testing. It has to be replicated. That's key, because if it's not replicated, then for whatever reason, one lab found it and the other one did not, then it's probably not true. You need to be able to test the hypothesis. This is, again, all this stuff is essential. I tend to say, again, a lot, but you have to be able to test the hypothesis. If you can't test it, if you can't test a theory, then it's a bad theory. I mean, we could say there's no such thing as gravity. It's actually little tiny, imps holding things together with magical cords. They're beyond any way of testing. There's no way that in our technology that we can do that. Well, that could be true, but we have no way of testing it. Therefore, it's not a good theory. It also needs to be falsifiable. You have to show your theory has to have the ability to be shown to be untrue. And that's kind of a hard thing for people to do, right? I mean, you want your theory to be true. It's kind of a natural thing. We all want it to be right, but really you have to have a theory that is proved is falsifiable. And simplicity. The simpler the theory, the more likely it is to be true. And here we are, just kind of another one of that. You discard the theory or revise it, test the revision. This happens all the time, right? I mean, this is sort of the whole idea. Let's see, that's about it. So 6 steps: scientific method, form the hypothesis. What do you think is going on out there? Conduct a literature review, including a review of the literature, a review of finding the systematic reviews, which is key. That's one of the things that I'm having you do. It's pretty cool. Let's see, there's page 35 points. I'm going to make sure I have my book handy, by golly. Conduct a study, analyze the data, and then report the results. So on the page 35, I'm going to get to the page here. With the points that they have. Results, replication, finding. Replication, yeah. So it's an increasingly important topic in science. A few decades, seen an explosion of research findings, particularly in medicine. One week we hear about some finding, the next we hear about conflicting finding. Does coffee give you cancer or help prevent it? Hard for non-experts to know what to believe in such phenomena. Recently, numerous scientists called for new efforts to increase the likelihood that published studies are true. So the point here is that if you're getting so many studies, which is true, you're having to do this, that some of them are going to have conflicting results, which is that's again sort of the nature of science. Another sort of bad thing about psychology here, they looked at 100 studies that were repeated, and only 39% of those 100 were replicated. So it has strong reaction from many psychologists that some of the findings in psychology were not replicated, which is kind of a concerning thing. I think my hypothesis or opinion, probably be more the case, is that there's so many variables within psychology. There's so many things that go into any particular behavior that it's hard to settle on one particular. This causes that. There's so many things influencing that, so many thises influencing that. It's going to be hard to focus those. But that's kind of an opinion, well, we'll see what happens with that. And here's a picture of that. Cell phone use impairs driving ability. It totally does, by the way. Don't do that. Yeah, this would be hard to do. We talked about having ethics in the syllabus. This would be the first ethical research thing that we talk about. So you're not really have a survey, maybe naturalistic observation. You're just sort of watching them on the street, how many people are using their cell phones, and seeing how many of them crash. That'd be kind of hard to do, but you could. Perform an experiment, and that one would be unethical. Have some people driving along the road using cell phones, others not, doing that on purpose. When you're risking that level of danger, that would be an unethical research. So variables. This is what you need to have, is variables within your studies. So it can be varied and it can be measured. This is the independent and dependent variable. That's with experimental design. You won't necessarily have independent and dependent with correlation design. And we'll get to what those are in just a little bit. So basically, independent variable is what you change as the researcher, and the dependent variable, it depends on independent variable like it's changed. So that's it depends on, I think, is a good word for that. So let's say an independent variable. This is kind of an easy one for folks, so I use it a lot. You have medication versus placebo. So active medication versus placebo. The independent variable is that, active medication versus placebo. And the dependent variable is, does the person get better or not? So that's the idea. You have to operationalize a construct, and this is something that you want to, if you take too many classes from me, which I don't know if they can take too many classes from me, but actually, I have a lot of students who take all my classes. So operationally define a construct. So how do you measure something like courage? Is there some way of measuring courage? Well, yes, there are. How about depression? Yes, there are. And they're pretty accurate. They have reliability and validity. There's like the Hamilton Depression Scale, Beck Depression Scale, all these different kind of scales that can, surveys, and people fill them out, either the treating physician or the patient or client, however you want to describe that. But they're pretty reliable and valid. So yes, you can operationalize the construct of depression using various scales. Now we're going to go into some various types of studies. And so there's quite a few different types, as you might imagine. A case study or case series could be. A case study is like one person. Case series is a few that you just. It basically falls under the I have observed. I like to say in science the more important thing is not eureka, that we have a discovery. The most important thing in science is, that's weird. So you notice something, that's kind of weird, and sure enough, yeah, and that's where it starts. You do a case study. This is one of your Truly's claim to fame. This happened pretty early on in my career, but it happened, so I feel kind of good about that. There's a medication called Clozaril for schizophrenia, for psychoses, and it came out in the early 1990s, late 1980s, excuse me, late 1980s, early 90s, somewhere in there. In any case, there's a type of schizophrenia where people drink a lot of fluids, a couple of gallons in 15 minutes kind of thing. And that's not good, right? Your sodium level drops, you get delirious, and people died from that. Well, I noticed that people that I placed on Clozaril who did that stopped doing that. I was like, that's weird. So I actually did write that up. It got published as a letter to the editor, but I'm okay with that, in the Journal of Clinical Psychiatry. And sure enough, after more years of research, Clozaril is now the treatment of choice for, it's called polydipsia hyponatremia. You drink a lot of water and your blood sodium drops. That's kind of cool. Naturalistic observation. You can just sort of watch people. I teach research methods in the fall. So I have people do naturalistic observations. One, the naturalistically observed door opening behavior. They just didn't try to change behavior. They just kind of watched people opening doors, like being polite. And they found, not to many people's surprise actually, that younger people didn't open doors for each other. They just kind of walked through. But that was naturalistic one. A participant, you kind of get with them. And we'll show some of that in a second here too. Coding overt behaviors. The open the door coding was pretty easy. It's whether or not they open the door. That's sometimes it's a little bit more difficult than that though. Reactivity and the Hawthorne effect. Basically, if you know you're being watched, you know you're being measured, you'll change your behavior. Hawthorne, I think we have a picture there. Hawthorne is well, they're going to see work efficiency at some company, but the people at the company knew this was going to happen, and they improved just because they knew it was happening. Observer bias. If you expect this, back to schemas, if experimenters expect to see something, well, sure enough, they'll be more likely to see it. So you really have to be cautious around those sort of things. And here's a case study. Let's see, I don't have much to say about that. It's in your textbook. And here's participatory. They're getting fish with the, I think they're probably, I don't know where they're from, probably Amazonian natives. By the way, we'll get to IRBs, institutional review boards, in a little bit, but Native Americans have their own IRBs now, because they got a little tired of people coming in, doing research, and leaving. So they have to really show that what they're doing is going to actually benefit the people. There's James Goodall. You may have heard of her. She studied chimpanzees. And here's the hawthorn. So being observed, change your behavior. They will make change your behavior to make yourself look good. So that's the hawthorn effect. Here's experimenter expectancies. This is a really cool thing. Basically, they told college students, you can see that they're trained rats to run a maze. Some students that said that rats were very bad at running mazes, and the other ones were told that they're very good to run mazes. They weren't, of course. The rats were the same, but they were told poor or good. And sure enough, the ones where the rats were told to be that they were good at running mazes actually ran mazes faster. So that's pretty interesting. Why, we don't know. Probably the expectations of the researcher had the rats somehow guided them, I guess. I don't know how you would even do that to a rat, but sure enough, it did change behavior. But look at one thing, 1963. Hell, I was young then. So that's a long time ago. Cool, it's a cool experiment. I don't know if this has been replicated. I don't know, but in any case, this is a pretty old one, 1963. Not that old, given this after I was born. So longitudinal cross-sectional. This is something I also have extra. So let me see if I can do this here. So this is time, and this is age. Okay, so we need to have a few different colors here. Excuse my delay. How about yellow? And one more. How about green? So I'll go back to red. So cross-sectional. So this is like 3 age groups. Okay, 3 age groups. The older age of blue, then yellow, then green. They age, of course, as they go across time, obviously. But so cross-sectional, you have a kind of a cross-section. Okay, you go across it. Now, that's good. The advantage of that is that you can do it more easily, right? Because you just have one time that you do it. The disadvantage is you don't really know if it's due to aging, like the blue being older than the green, or due to the time that the cohorts were born. I use the example of cell phones, or whatever, that younger people can text better than older people, not because of their age, but because they grew up texting. So it was something that they were used to doing. Longitudinal is better to see the effects of age, but it's hard to do because people drop out, people move, research funding goes away, all those sort of things will influence longitudinal studies. So it's better because they're seeing more what's going on with age-wise, and difficult because they take longer. So questionnaires, this is common. People have questionnaires on everything. There's like thousands of psychology tests, literally. And you have to watch out that people want to make themselves look good, right? So you may have some bias in self-reports. Correlational. Let's see, we've got to get the correlation here. Yeah. So positive and negative correlations. Positive correlation, when this one goes up, that one goes up. On big arrow. Negative correlation, when let's see, when this one goes up, this one goes down. If that makes any sense. So, nope, let's see. Actually, screw that. this way. That's what I mean. Do we have an eraser? I think I have an eraser here somewhere. There we go. That's a negative correlation. So negative and positive. So now we don't know which causes what. Okay, color correlation does not equal causation. It could be that, so we don't know which causes what, but there might be something completely different, the third variable that causes both. That said, you can get a lot out of these, and sometimes it's good enough to know if something's correlated. The example I use here is there's a correlation between hopelessness in people who are depressed and suicide attempts. Okay, so we know there's a correlation there. Now, does suicide cause a hopelessness or vice versa? We don't know. That'd be a totally unethical thing to do. Get someone who's depressed and point out that the life is indeed hopeless and see if they are more likely to kill themselves. No, we're not going to do that. But we can intervene, sort of. We're not doing well with our suicide prevention stuff, that's for sure. But that's a different issue. We can intervene psychotherapeutically to have suicide, to treat the hopelessness. And actually, good psychotherapy has been shown to decrease suicide. So that's the ethical need for correlation. And after then, that's the clinical usefulness of being able to predict the suicide. And here's one. Now, the discussion for this week is, what is science proven? That's kind of the trick question is statistically. Okay, science uses statistics. And so it's likely the findings that you have actually do represent the external world, but it always gets down to statistics. There's like a small chance that they do not, that it was just random finding. And that's the nature of science. That's the very nature of science. Is there's always a chance that it was random, and what you think is happening is actually not happening. Now, do we know that cigarettes cause lung disease? Well, statistically, there's might be a 1 in, I don't know, quadrillion chance that they don't, something like that. But of course they do. Of course they do. We know when people stop smoking, the risk of lung cancer goes down, et cetera, et cetera. So that's the idea. And here's what I just said. This one, there's no correlation. I think we have more of these. Positive and negative. So experiments. Now this is when people say experiment, they usually think of any kind of science as experiment. That's not true. Experiment is a very, very specific type of research. Okay, in experiments you have a control group, an experimental group, independent and dependent variables, and you try to control as many variables that you can. So let's say, well, let's see. How about we'll use medications again. That's a common one. People can sort of relate to that. So I have med, placebo. Okay, and then you have that's your control is placebo. Experimental is the med. Then you give it to a bunch of people and see if their depression improves or not, or whatever. Depression, high blood pressure, cancer, heart disease, whatever. So that's the idea. So the dependent is the independent is when you independently change, and the dependent, but again, the color here, dependent is depending on which one they got. It'll change one way or not, the other, or not. There may not be any effect. When I was in med school, I had an opportunity to be a part of a study, and it was I got paid, right? So you get paid to do these things, and I needed money, so I could pay like $175 to not eat anything, take either placebo or a medication, swallow. I think I had to swallow like 10 aspirin, like a lot of aspirin, because aspirin causes bleeds in the stomach. Okay, it causes your stomach to bleed, and that's bad. If people have to take aspirin, their stomach bleeds, that's not good. So I did that. And then I got endoscopy. I got a tube down my throat to see how much I was bleeding. And I got to watch this, actually. It's kind of cool. How many people can see those inside of their stomach? I was bleeding like stink. I mean, blood was just like oozing from my gastric mucosa. And it was like, oh, that's bad. But it went away once I stopped the aspirin, of course. course. But so I either got placebo or that medication did not work, and I don't know which one I got. But it was, anyway, an illustrative anecdote. And here's what I just said. Either supports or does not support the hypothesis. In my research methods class this last semester, people talked about how in high school, they'd have to do these kind of studies, and they were told that if it came out positive, that it actually supported the hypothesis, that they would say science has proven something. That's too bad that that's taught like that, because science does not prove things. It increases the chances of whatever you're seeing as being true, as being likely or not. So you reject the hypothesis, the null hypothesis, or you fail to reject the null hypothesis. That's the idea. So science, it makes things really likely, okay? But as far as proving what's out there, not quite. So who are you going to study? How am I doing? I think you're doing pretty good here. Kind of watching the time, making sure I have I think these are usually going to go about 45 minutes to an hour. So you can't study everybody, okay? So let's switch over. How about Alzheimer's? We're going to study Alzheimer's. And so can we study every person with Alzheimer's on the planet? No, of course not. But we can we can sample that population. Okay, we can take a sample of people who have Alzheimer's and see if we can study them to see if we can prevent it or not, or prevent it getting worse. So we want it random, meaning we don't want to pick people who have a better prognosis, say, to make our drug look better. No, that's unethical again. You want to have random sampling. Lots of times it's convenience, okay? Convenience sample. I'm tired of that color. Let's go to green. So convenience is that they're right there. So they're right there. They're convenient. Might as well use them, given that they're like right there. Switching over some, a lot of research is done on college students because they're convenient. A lot of PhD students will study introduction to psychology students. Well, that's nice. They're convenient, but are they generalizable? Okay, is it the studying college students generalized to the rest of the population? Not completely. People who go to college are different than people who don't go to college. So it may not be generalizable. Although it depends on the college too, right? I like using Helena College as compared to Carroll College. The population that goes to Helena College is much more representative. It's a representative sample of, say, the greater Helena area. People who go to Carroll College tend to not be. They tend to be younger, tend to have more money, tend to play more sports, all that kind of stuff. They tend to be more religious. So when it comes to the representation of the general population, Helena College is a more representative sample than Carroll. And here's some figures showing that. Here's a bunch of people. Random, you just kind of randomly get people. Convenience, you just take the ones who are out front. Kind of funky little pictures. And random assignment, control versus experimental. Randomness is you want to make sure you don't get some kind of bias, right? That's the idea. So, and here's some methodology. We'll see these again next chapter, these pictures, because I just think they're cool pictures. This is EEG. It takes your brain waves, picks up your brain waves. This is an actual brain. This is an actual person. They took the skull off from the skin. They do this for like seizures. Okay, when people have really bad seizures, you can go in and find out where the seizure starts, the locus, and kind of cut out that little part of the brain. It's usually pretty small, right? Usually just a tiny chunk of brain. So, and then the seizures go away. But while they're trying to figure that out, they go in and they stick all these electrodes into the brain, which, you think that'd be dangerous, but not really. I mean, they kind of go through and the brain can repair itself to some degree. So they have to sit there in a hospital bed for like a week with the electrodes in your brain. How cool is that? So would you do that? How many people would do that what would it take to do that? I would probably need more than $175 to do that. I'd probably do it for $25,000 maybe. If I got paid 25 grand to have them take off my scalp and skull, They put it back on. It's not like they leave it off. It gets replaced later. Have these electrodes placed into my brain, lie in bed for a week, letting them see where my brain goes, and put it back. Yeah, I don't know. I'd probably do it for 25 grand. Yeah, probably not. It might take like 250 grand. I would do it for that. So, and some other ones, brain scans. This is showing the difference between controls and ADHD. This is that's the wrong color for this slide, isn't it? How about we'll go back to purple? I like purple. So this is part of the motor pathway. Caudate nucleus is what it's called. So you can see people with ADHD, there's not as much activity. What that means is that's where their attention has deficits. This actually sort of decreases hyperactivity, right? They have more control here than there. So that's showing that people with ADHD, that part of the brain is decreased. This is this up here, actually. So it's more blue opposed to green. So now I think, well, yesterday, talking about how brains, we'll see brain activity corresponds to the various behavior activity, and of course it does. Of course it does. What else would it be? So I like pointing that out. And same. People with schizophrenia have decreased activity up here. And I need the color for that. I'm going to have to change colors a lot here today. So this is so-called hypofrontality. That compared to that. Okay. So hypofrontality. This is the frontal lobe. Okay. Frontal lobe. And people with schizophrenia, their frontal lobes aren't as active. That's called hypofrontality. When we get to chapter 14, we'll talk about negative symptoms. So negative symptoms. Negative symptoms of schizophrenia is lack of motivation, lack of planning, lack of emotional expression, things that are lacking. So hence negatives like subtraction. And those are due to the decreased activity in the prefrontal cortex. And so when we get to chapter 14, you'll hear that again. We now are using distributed learning. TMS is way cool. Oh, back here. TMS is way cool. Transcranial magnetic stimulation. They can go in and just like turn on a section or turn off a section of brain, given depending on the magnetic coil and where the field is going. So magnetic fields are very precise, right? I mean, they go from here to here. So instead of going throughout the brain, they're turning on or turning off very specific parts of the brain. It's pretty cool. It's used more and more for treating mental diseases, actually. Depression, anxiety are both FDA indicated. That you go in and get this stuff, get a little TMS, and it treats it pretty well, actually. People who are refractory to medications will go in and get TMS. I know there's some psychiatrists that this is all they're doing now is TMS. They're just doing transcranial magnetic stimulation for depression and anxiety and whatnot. So yeah, there's lots of studies on it. They're looking at it for alcohol use disorders, obsessive compulsive disorder, schizophrenia, Alzheimer's, all kinds of stuff. This stuff is the TMS is looked for. They're turning on or turning off parts of the brain. So pretty cool. It's way cool, as a matter of fact. IRBs, animal research. Animal research is actually, they have more protections than humans because they can't say no, right? They can't say, no, I don't want this to happen. So, but you think about it though, University of Montana, by the way, University of Montana has like a huge mouse lab. And I got to tour it. So I'm actually on the Institutional Review Board at the University of Montana. So I got to go and tour their mouse lab. It's pretty amazing. It's like huge, right? There's like all these mice in these cages. And when you think about it though, I mean, it's not a bad life for a mouse. They don't have cats eating them. You don't have people trapping them. They live in these nice cages. They get cleaned. They get food. Yeah, they get told who they have to reproduce with, but that's not that bad. It's like arranged marriages or something, right? So anyway, that's animal research. They also, I mean, mice are used a lot. Guinea pigs are not used much, by the way. People say, I must be treating me like a guinea pig. It's like, well, they don't really use guinea pigs in research, not much. So no, you're not treated by guinea pigs. By the way, guinea pigs are a domesticated animal in South America, from what I understand, and they use them like chickens. They raise them and eat them. So if you're being a guinea pig, you're actually being consumed. You're accusing somebody of cannibalism. So now you know. So lots of stuff in the IRBs. There were some pretty unethical studies that occurred however many years ago, and the IRBs are arranged to counter that. So a few things. There's privacy. Your identity needs to be private. Access to data. Who has access to the data? Some can, some shouldn't. Informed consent. Okay, you have to know what you're getting yourself into in the study. You have to be able to say, oh, yeah, I get it. I will consent to do this or not consent to do this study. Deception is like rarely used. You're saying you're studying something, but you're actually studying something else. So you really have to justify deceiving somebody. I've been on the IRB for quite a long time. Actually, I think I'm the longest member of it, which makes me think maybe I should give it up and have somebody else on the school do it, but I don't think anybody else wants to. But that said, I don't think I've ever seen a place where deception was used, and I've seen a lot, right? We've done this for quite a while because there's no real reason for it. So risks and benefits. So this is what's the risk to the person? Let's go back to the door opening behavior observation. There's really no risks or benefits to that. They were just watching people open doors and observation. So there was like no risk or benefits anywhere. But how about something, say, how about people who are getting the vaccine for the SARS-CoV-2, which is the name of the virus, by the way, not COVID. COVID is the disease caused by the virus, but that's okay. But that's kind of hell of a thing, right? So I'm going to take this vaccine and see if I can get infected. Well, we don't know what the risks were, and we didn't know if there's going to be any benefits. That was the whole point. So I'm sure that one got an IRB. Taking a look at that one, they probably did. By the way, that new vaccine looks really promising. It's really cool. It's like finally some good news, man. But yeah, it looks good. This looks like it's pretty safe. Looks like it's pretty effective. So I mean, it's going to be a logistical thing to get it out to everybody, of course. But wow, if they can, then they will. We'll figure that out. Then that's really hopeful. Hopefully people will take it. Respect for persons. You can't treat them like dirt. You have to show them why they're important. And this occurs to you can't have somebody be part of a study just because they're convenient if they're at risk for something. So say they're prisoners. Yeah, they're right there. What the hell? Let's go ahead and just, we're going to subject these prisoners to whatever test because, well, they're right there. What the hell? That's bad. That's bad. So no, you can't do that. That said, if you do have a study that targets prisoner behavior, say recidivism, something like that, that might make sense. Okay, so that it makes sense. You're not just using them because they're handy, whether you actually have something that might be useful for your study. Culturally sensitive. This is now Native Americans are the largest minority in Montana, so we think we'll talk about them the most. But is it are you being culturally appropriate while working with folks? That's again sort of a large issue. And here's different cultures. That's all you need for that, I guess. So evaluating the data, you have internal, external, face, predictive, and constructive. That's validity. Validity means the test you're using, the operationalization of your construct. Okay, you got to be able to say that sentence. You operationalize your construct. Does it actually measure? Does your test actually measure what you're saying it measures? Is it valid? In some things, hopefully it is. Is it valid inside the test to external? Does it look like it's valid just in general? That sort of idea. We had just this last semester, a student study mask wearing behavior, and this is a pun that is intended because she was looking at whether or not people were wearing masks and looked at Murdoch's, Capital Sports versus Real Food Store and Natural Grocers, and sure enough, as you might imagine, fewer people were wearing masks in Murdoch's and Capital Sports than were in the health food stores. So we wondered if this observational study had good face validity. Does it predict stuff? And is it does it predict whatever sort of thing? Sorry about that. Reliability. Can you trust whatever it is? So you test it once and test it twice, you get the same results. That's test retest. Iterator. One person tests and another person tests, and they get the same results. And again, predictive. Does it have can it predict the future kind of thing? So here's some cool statistic stuff. Everything varies randomly. Okay, nothing is completely stable. This is it can be sort of unnerving when you think about this too much. That there's things don't stay stable. There's there can be random error, things that just change randomly. We don't know why. Systematic error. Every measurement that you do kind of changes slightly. And standard errors. This is the limitation of measurements. There's, we'll look at error bars a lot, standard errors. Type 1 and type 2 errors. So this gets kind of confusing, but I actually had it explained to me finally that it made some sense. I'm going to go to red. I like red. It's sort of the better color for this. So type 1 error, you reject the null hypothesis when it is true. What that means is you think there is a relationship, but then in reality, okay, when in reality what's out there, there is not. So it's basically a false positive. Okay, so type 1 error is a false positive. You think there's a relationship out there, but in reality, there's not. A type 2 error is you reject the null hypothesis. You think there's nothing out there. There's no relationship, but there actually is. Okay, so that's a false. This is hard to do, by the way. Negative. Okay, so now I like people to think about these type 1 and type 2 errors some. But what that means is you're testing something, you're getting statistical information about them that supports or that supports or does not support your theory. And you, by doing that, you either reject or accept the null, or fail to accept. Fail to reject is actually where you're supposed to say that. Fail to reject the null hypothesis. And so that means what's out there is what's out there in real world is only sort of measurable. Okay, it's only sort of measurable, but we get pretty close, and we have all kinds of toys and medicines and stuff like that that we can use with it. But strictly speaking, it's still out there. Now, here's a stats joke for you. People don't like having type 1 errors, rejecting null hypothesis when it's actually true. So the less likely to have a type 1 error, the more likely it is to have a type 2 error. That's just so funny. The more likely, that's the reason that's a joke is it's a joke as to the inherent inability to completely measure the external world. So the less likely you have a type 1 error, the more likely you have a type 2. So here's the story behind that. I took a class in biostatistics that actually was in epidemiology last spring, 2 springs ago now. Holy crap, time goes on. And the instructor said that, and we both guffawed. It's like, yeah, you don't get much nerdier than that, folks. You really don't get much nerdier than that. that's about top of the line nerddom. So descriptive, you summarize the data. This is me, so you have means, standard deviations, all that kind of stuff. You then have central tendency. You have the mean, median, and mode. Mean is the average. You take all the scores and divide by how many scores there are. Median is half the numbers fall above and half the numbers fall below a certain point. Median is good for like house prices. You probably see home prices. They always say the median home price. That's because there's some like stupid expensive homes. And if you add the, and super cheap ones too, I suppose. So if you added them together and got the mean, it would be way higher than the actual value that's useful. So they use the median home value. And mode is the thing that happens the most often. There's some statistics for you. And here's variability. This is the standard deviation. These little bars here, I will point out throughout much of the semester. what this means is this is the mean. Okay, that's the mean, the average. And we're pretty sure that the actual mean, okay, is somewhere between here and here. Okay, so that's the standard deviation. So also there's confidence intervals too, which is probably more gives you more information than standard deviation. So confidence interval, what that means is I am 95% sure, we'll just use 95 because that's the average, 95% sure that the real mean lies somewhere between those 2 points. So think about that as well. Okay, we're 5% not quite sure that's what it is. Okay, so that's a pretty cool thing in science, is that we have this confidence interval. So confidence intervals is usually abbreviated as CI. So that's again, it's a limitation. It's an inherent limitation to science. We're not going to get better at that. Okay, it's just not getting better. It's not like you can improve the ability to measure the external environment. You can improve your constructs. You can improve how you operationalize your constructs. Those you can improve and get a better idea, but you're always going to have these confidence intervals, standard deviation, and statistics. Here's the correlations again. This is a better scatter plot. So most of them will look something like this. Unless there's absolutely no relationship, then they look like that. Positive and negative correlations. Now, inferential statistics. So the smaller this is the p-value, okay, also called p-value. The smaller it is, the less likely that study that you did found something, it's less likely it had a type 1 error. Okay, remember the type 1 error? There we are. So it's less likely that you rejected the null hypothesis when it's actually true. So this is like what, 1 in 20, 1 in 100, 1 in 1,000, 1 in 10,000. So the smaller the p-value, the less likely that study has a type 1 error. Okay? So when I say the significant in your syllabus and that was funny, this is why it's funny, because it's relating the terms to p-values. Okay, so it's not that funny. And finally, meta-analysis. This is where you study studies. There's there's a movement afoot to really look at common data. That there's common places where data is given, sort of stored, and then people can get all that data and we can get their own large study from it. All right, so that's the end of that. I don't want to keep that. Let's go to, where's my teams? I'm going to stop the recording. Any questions before we go there, Scott? I'll stop the recording.
Okay. Yeah, just one, I guess. On the chapter test, we have two